And just for fun, let's say that you travel to the year 2045, where space travel is just as common as flying cars are today. And had a spaceflight conversion done on your DeLorean so that you and your date could go watch the full life of a star unfold right before your very eyes. What would you see on this romantic excursion?
Initially, you'd see a nebula, a cold, molecular cloud of gas and dust. Then you'd watch as the molecules in the nebula spin and collapse in on themselves under the influence of their own gravity to form a protostar, a warm, spinning ball of gas and dust.
Now, if you picked a puny nebula, all that spinning and crunching would lead to nothing but a decidedly unromantic substellar brown dwarf.
Brown dwarfs don't give off any light or heat, so they look more like a lonely Jovian planet than a star.
So let's say you picked a nebula with enough mass to create a full-fledged star.
After a while, you'd see that protostar release an enormous amount of energy in the form of light, heat, and radiation as it began a serious fusion reaction and transformed into a mature, main sequence star. The star will spend 90% of its lifespan in its main sequence, which accounts for about 10 billion years for a typical star.
Now, nuclear fusion, as its name suggests, is the fusing together of two nuclei to make a new element.
So, the hydrogen your star began with fuses together to create helium. So naturally, the star will eventually run low on the hydrogen it's been burning and cool down enough for gravity to pull the outer layers in closer, which, of course, means the star is going to get hotter again as that gravitational potential energy is converted into kinetic energy. This heats the middle layers up enough for the hydrogen to fuse together and become helium. And in the core, it's going to get so hot that the helium produced in the first fusion reaction will start to fuse together and create carbon. Fusion is also going to make the star's core so hot, the outer layers expand until the star becomes a red giant. To give you a sense of scale, when our sun expands and becomes a red giant, it will swallow up the terrestrial planets in the process. Then, once the helium has run low, the star is going to collapse and expand again. Only this time, if you've got a small-sized star, it will expand so fast that it throws off its outer layers, creating a planetary ring-shaped nebula around its now exposed core. At this point, the core itself has become a white dwarf, a stellar remnant so dense it packs nearly the full mass of a star into a sphere the size of our Earth. Where it once burned bright, producing light through a massive fusion reaction, it now glows like a piece of white-hot metal just pulled from a fire, producing light as it releases thermal energy stored up in its glory days. Eventually, the core will cool until it goes completely dark and becomes a black dwarf.
But let's say that the star that you're watching is unusually massive. In this case, gravity is strong enough that the star will keep expanding and contracting. And each time the star contracts, it'll create more heat until it fuses more of its elements together into the next heavier element on the periodic table until it reaches iron. Then, like all stars, it will die. But since the star you're watching is particularly massive, it'll be an awesome death.
Exploding as a supernova, creating even heavier elements in the process and ejecting enough matter back into space to potentially form a new nebula capable of producing new stars. Meanwhile, the remaining core material lives on as a neutron star, a star so dense it packs twice the mass of our own sun into a sphere roughly 14 miles in diameter.
If the star was even more massive, it will become a black hole. Black holes pack the mass of 3 or more of our suns into one single, infinitely small, infinitely dense point.
So let's hope the star you've been flying your DeLorean near isn't destined to become a black hole. Because no carefully timed lightning bolt, no supercharged locomotive, no anything is going to get you moving fast enough to fly back to Hill Valley. Not even light can escape from the collapsed massive stellar core we call the black hole.